Top 25 AI coding interview questions and answers. Artificial intelligence coding interviews evaluate your technical knowledge, programming skills, and understanding of machine learning concepts. These questions will help you prepare effectively for upcoming AI developer or engineer interviews. 1. What is artificial intelligence? Artificial intelligence, AI, refers to the simulation of human intelligence processes by machines, particularly computer systems. These include learning, reasoning, and self-correction. AI applications include natural language processing, expert systems, speech recognition, and machine vision. The goal of AI is to enable computers to perform tasks that typically require human intelligence. AI systems rely on algorithms and data models to improve performance over time through iterative learning and data-driven optimization techniques. 2. What is the difference between AI, machine learning, and deep learning? AI is the broad concept of machines performing human-like intelligence tasks. Machine learning, ML, is a subset of AI focused on learning patterns from data. Deep learning, DL, is a subset of ML using neural networks with multiple layers to model complex relationships. While AI encompasses all intelligent behavior, ML and DL are techniques that enable AI to function efficiently through data-driven learning and feature extraction. 3. What are neural networks? Neural networks are computational models inspired by the human brain, consisting of interconnected nodes or neurons. They process data in layers, where each neuron transforms inputs into meaningful patterns. Neural networks are widely used in tasks like image recognition, speech processing, and natural language understanding. Through learning algorithms like backpropagation, they adjust weights to minimize errors. Their deep variants, called deep neural networks, power advanced AI systems, including computer vision and autonomous technologies. 4. Explain the concept of supervised learning. Supervised learning is a machine learning approach where models are trained on labeled data. The algorithm learns to map input features to the correct output by minimizing prediction errors. Examples include classification and regression problems, such as spam detection or predicting house prices. Supervised learning requires a large, representative dataset and employs algorithms like linear regression, decision trees, or support vector machines to improve accuracy through iterative training and validation. 5. What is unsupervised learning? Unsupervised learning deals with unlabeled data, where the algorithm identifies hidden patterns or relationships without predefined outputs. It's primarily used for clustering, dimensionality reduction, and association tasks. Examples include customer segmentation, anomaly detection, and market basket analysis. Common algorithms are k-means clustering, hierarchical clustering, and principal component analysis, PCA. The goal is to discover structure within data, providing insights for further analysis or as input for supervised learning models. 6. What is reinforcement learning? Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by interacting with its environment. It receives rewards or penalties for its actions and aims to maximize cumulative rewards over time. RL involves key components such as state, action, and reward. Popular algorithms include Q-learning and deep Q networks, DQN. RL is widely applied in robotics, gaming, autonomous driving, and real-time decision-making systems requiring adaptive intelligence. 7. What are the main types of neural networks? The main types of neural networks include feed-forward neural networks, FNN, convolutional neural networks, CNN, recurrent neural networks, RNN, and generative adversarial networks, GAN. FNNs handle general tasks. CNNs specialize in image processing. RNNs work with sequential data like text or speech. And GANs generate synthetic data. Each network architecture is tailored to specific data structures and problem types, allowing AI systems to perform complex recognition, prediction, and generation tasks effectively. 8. Explain gradient descent. Gradient descent is an optimization algorithm used to minimize a model's loss function by iteratively updating parameters. It calculates the gradient, slope, of the loss function with respect to each weight and adjusts them in the opposite direction. Common variations include batch, stochastic, and mini-batch gradient descent. The learning rate determines step size, balancing convergence speed and stability. Gradient descent is fundamental for training neural networks and other machine learning algorithms efficiently. 9. What is overfitting in machine learning? Overfitting occurs when a model learns training data too well, including noise or random fluctuations, resulting in poor generalization to new data. It performs well on training sets, but fails on test sets. Techniques like cross-validation, regularization, dropout, and early stopping help prevent overfitting. Balancing model complexity and data diversity ensures better generalization. Overfitting is a common issue in deep learning when datasets are small or model architectures are overly complex. 10. What is underfitting in machine learning? Underfitting happens when a model is too simple to capture underlying patterns in the data, leading to poor performance on both training and test sets. It indicates insufficient model complexity or inadequate training. Solutions include increasing model parameters, adding more relevant features, or training longer. Using more advanced algorithms and ensuring proper feature engineering can help reduce underfitting. Balancing bias and variance is essential for optimal model accuracy and generalization. 11. What is a confusion matrix? A confusion matrix is a performance measurement tool used for classification models. It displays actual versus predicted outcomes in 4 categories: true positive, true negative, false positive, and false negative. From these values, key metrics like accuracy, precision, recall, and F1 score can be derived. The confusion matrix provides insight into model performance, particularly when evaluating imbalanced datasets. It helps identify strengths and weaknesses in classification-based AI models and guides model improvement strategies. 12. What is regularization? Regularization is a technique used to prevent overfitting in machine learning models by adding a penalty term to the loss function. It discourages large coefficient values, ensuring smoother generalization. Common regularization methods include L1 lasso, L2 ridge, and elastic net. These methods control model complexity, making predictions more robust on unseen data. Regularization plays a crucial role in maintaining model accuracy, especially in high-dimensional datasets with numerous correlated or redundant features. 13. What are hyperparameters in machine learning? Hyperparameters are configuration settings set before training a model that control its learning process. Examples include learning rate, number of hidden layers, batch size, and number of epochs. Unlike model parameters, which are learned during training, hyperparameters are manually tuned to achieve optimal performance. Techniques such as grid search, random search, and Bayesian optimization help identify the best combinations. Proper tuning ensures models learn efficiently, balancing accuracy, speed, and generalization capabilities effectively. 14. What is a loss function? A loss function measures how well a model's predictions align with actual outcomes. It quantifies the error and guides optimization during training. Common examples include mean squared error for regression and cross-entropy loss for classification. The goal is to minimize this loss through iterative updates using algorithms like gradient descent. Selecting the right loss function is critical for ensuring stable learning and achieving accurate, generalizable AI model performance. 15. What are activation functions in neural networks? Activation functions introduce nonlinearity into neural networks, allowing them to model complex patterns. They determine whether a neuron should be activated based on weighted inputs. Common examples include sigmoid, tan, and ReLU, rectified linear unit. ReLU is widely used due to its computational efficiency and ability to reduce vanishing gradient issues. Choosing the right activation function ensures better model learning, stability, and convergence during training. 16. Explain the role of backpropagation. Backpropagation is an algorithm used for training neural networks by minimizing the error between predicted and actual outputs. It works by propagating the error backward through layers, updating weights based on gradients. This process helps the network learn optimal parameters. Combined with gradient descent, it adjusts weights iteratively to improve prediction accuracy. Backpropagation is the foundation of deep learning and enables efficient training of multi-layered neural networks for complex data-driven applications. 17. What is transfer learning? Transfer learning involves using a pre-trained model on a related task to improve learning efficiency on a new task. It's especially useful when data is limited. By reusing learned features from large datasets, models achieve better accuracy with less computation. Common frameworks like TensorFlow and PyTorch support transfer learning with models, such as ResNet or BERT. This approach accelerates development and enhances performance across image recognition, NLP, and other AI applications. 18. What are generative adversarial networks, GANs? GANs are AI models consisting of two neural networks, a generator and a discriminator, competing against each other. The generator creates synthetic data, while the discriminator distinguishes between real and fake samples. Through iterative training, both networks improve, leading to highly realistic outputs. GANs are widely used for image generation, data augmentation, and creative AI tasks. Their adversarial learning process makes them powerful tools in generative modeling and simulation tasks. 19. What is natural language processing, NLP? Natural language processing, NLP, enables computers to understand, interpret, and generate human language. It combines linguistics, computer science, and AI. Applications include chatbots, sentiment analysis, and machine translation. NLP involves processes like tokenization, stemming, lemmatization, and named entity recognition. Deep learning models such as BERT and GPT have revolutionized NLP by improving context understanding. NLP plays a vital role in bridging human communication and machine comprehension through advanced AI techniques. 20. What is computer vision? Computer vision is a field of AI that enables machines to interpret and understand visual information from the world. It processes images and videos to detect, classify, and analyze objects. Techniques like image segmentation, object detection, and facial recognition are commonly used. Deep learning architectures, such as CNNs, power modern computer vision systems. Applications include autonomous vehicles, medical imaging, and surveillance. The goal is to replicate human-like visual perception through computational models. 21. What is feature engineering? Feature engineering involves creating, selecting, and transforming input variables to improve model performance. It enhances data representation and helps algorithms detect meaningful patterns. Techniques include normalization, encoding categorical variables, and creating interaction features. Effective feature engineering often determines a model's success, especially in traditional machine learning. It requires domain knowledge, data exploration, and creativity to extract relevant information from raw data, improving accuracy and interpretability. 22. What is dimensionality reduction? Dimensionality reduction is the process of reducing input variables while retaining essential information. It simplifies models, reduces overfitting, and speeds up computation. Common techniques include principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE. In AI, it's vital for visualizing complex datasets and improving performance on high-dimensional data. By focusing on key features, dimensionality reduction ensures more efficient and interpretable learning outcomes. 23. What is model evaluation in AI? Model evaluation measures how well an AI model performs on unseen data. It ensures reliability and generalization. Common evaluation metrics include accuracy, precision, recall, F1 score, ROCAUC, and mean absolute error. Cross-validation techniques provide deeper insights into model robustness. Model evaluation is critical before deployment, allowing developers to refine and validate performance. It ensures models deliver consistent, fair, and accurate predictions across diverse datasets. 24. What is a confusion between bias and variance? Bias refers to errors due to overly simplistic assumptions, leading to underfitting. Variance represents sensitivity to training data, causing overfitting. The bias-variance trade-off aims to balance both to achieve optimal model accuracy. High bias reduces flexibility, while high variance decreases generalization. Effective AI models find equilibrium by adjusting model complexity, regularization, and training techniques. This balance ensures strong predictive performance on both training and unseen datasets. 25. What are the ethical concerns in AI? AI raises ethical issues related to privacy, bias, transparency, and accountability. Algorithms can unintentionally reflect societal biases present in training data, leading to unfair outcomes. Ensuring fairness, interpretability, and security is essential. Organizations must follow ethical AI principles, including data governance and responsible model deployment. Addressing ethical challenges builds trust, enhances inclusivity, and ensures AI systems serve humanity positively without compromising moral or legal standards. Mastering these AI coding interview questions strengthens your foundation in machine learning, deep learning, and data-driven algorithms. Continuous learning, hands-on coding, and conceptual clarity will ensure outstanding performance in AI interviews.